Okay, now let's introduce the summation notation. In this case here, we're given a sequence A1, A2, A3, and so on. The nth partial sum, okay, so assume, let's say this is an infinite sequence. The nth partial sum, S sub n, is a finite series and is represented by S sub n is equal to the summation of A sub I. So this is the capital sigma, and this is used for summation notation, which is just telling us that we're summing up the first n terms of the sequence, and the I is the index. So this is our lower limit for the summation. This is the upper limit. This is the index. So I is the index, and we're indexing I from 1 to n. So this is, and we're summing all of them up. So this is telling us that we're summing up the first n terms of the sequence starting with A sub 1. So A sub 1, A sub 2, all the way to A sub n. So this is how we represent it using summation notation. Instead of writing out all these terms all the time, we can write it concisely using summation notation. Now, the sum of all of the terms in a sequence is an infinite series and is given by this notation. So the only difference is now we're going off to infinity. So the upper limit is infinity instead of n. So an nth partial term is given by this. The infinite series S is given by this notation here, and it represents this. Okay, and so now we're going to do some examples and then talk about properties of summations, which are going to be important for us.